Back to topic 1 of IB chemistry. We're now going to be continuing with topic 1.2, which is the mole concept. So let's get started. So in this topic, we're going to be learning about what are moles. And that's going to be very important for many calculations that we will do in this topic. So the mole is the SI unit for the amount of a substance. So amount is a very specific term in chemistry. In normal everyday life, when we talk about amount, we sometimes refer to masses or volumes, but amount in chemistry specifically only refers to the amount in moles. So that is a very important thing, especially when you're writing IAs and things like that and any papers. It's important to specifically say moles, or I mean amount, only when you're referring to moles. And 1 mole is basically 6.02 times 10 to the power of 23 elementary entities. So that could be atoms or the number of a specific molecule, etc. And that is the Avogadro number. So that is dimensionless. The Avogadro number is dimensionless, which means that it does not have any units. Whereas the Avogadro constant is not dimensionless. It has specific units, which are per mole, moles to the power of -1. Okay. So now moving on to relative atomic mass, molecular mass, and molar mass. So relative atomic mass, or AR, is the weighted mean mass of all the naturally occurring isotopes of an element relative to 1/12 the mass of a carbon-12 atom. This is a key IB definition, and it is examinable, so it's good to remember. Once again, this is dimensionless because it's on a relative scale, and we can calculate AR from some data if we're given some data, and this is the formula for that. So it is the sum of the product of the mass of the isotope times its relative abundance, all divided by the sum of all of the relative abundances of all of the isotopes. So if that is not clear right now, we'll do an example in the next slide, so do not worry. Relative molecular mass is MR, is the weighted mean mass of a molecule relative to 1/12 the mass of a carbon-12 atom. It's the sum of all of the ARs of the atoms in the molecule, and once again, it is dimensionless. So, and then finally, relative formula mass is used for compounds that don't form molecules, like ionic compounds, such as ionic compounds. So that is because in an ionic substance, it is, for example, NaCl. There is a 1-to-1 ratio of Na and Cl in NaCl, but that doesn't mean it's a molecule of 1 Na bonded to 1 Cl. It is a lattice of many, many Nas and many, many Cls, but they're in a 1-to-1 ratio. But since we cannot exactly know the number of each of those ions, we just go by the formula mass, which is the ratio. So, and if we want to calculate that, it is the sum of the ARs of the elements and the formula of the compound. Molar mass, M, is has units, grams per mole, and it is the mass in grams of 1 mole of any substance. And it is numerically equal to AR. So this is a practice question, IB past paper question. So remember we said that the formula is that AR is equal to the sum of the mass of each isotope, I'm going to abbreviate it like that, multiplied by each of their percentage abundances, divided by the sum of all of the percentage abundances. So that would be, in this case, 46 times 7.98 plus 47 times 7.32 plus 48 times 73.99 plus 49 times 5.46 plus 50 times 5.25 divided by 7.98 plus 7.32 plus 73.99 plus 5.46 plus 5.25. And they've said to give it to 2 decimal places. So this is actually equal to 47.9265. No units, remember. And we will round this to 0.93. Examiner exactly what number you've got and how exactly you're rounding it. Know that it's 2 decimal places, although it's given in the question. This makes it a bit friendlier to work with. Right, so now to calculate amounts in moles, we have these 2 formulas to calculate moles, and it is mass over molar mass, mass in grams, so you should convert it to grams if it's not already, and molar mass in grams per mole. Or we could do N equals CV, which is concentration in mole per decimeter cubed, and volume in dm cubed. So oftentimes in questions, they give the volume in cm cubed rather than dm cubed. So it's important to remember to convert it. So 1 dm cubed is equal to 1000 cm cubed. And cm cubed is basically a milliliter. 1 milliliter is equal to 1 cm cubed. But in chemistry, we tend to say cm cubed rather than ml. Right, and then we have this concept about molar ratios, which is also important for calculating moles. It's the coefficients in a balanced equation, which indicates the mole ratios of the reactants and products. For example, so this is a practice question, but before I read it, let's look at this equation over here. For example, if I asked the ratio of OH to pH3, it is a 3:1 ratio because there is a 3 here and there's no coefficient in front of the pH3, which means that it is actually 1. So just like in algebra, we don't really write 1x, we just write x. Here, we don't really write 1 in front of things unnecessarily, we just put nothing. So that's important when you're calculating moles of the products. So in this case, it's asking that there is 2.478 grams of white phosphorus, which is P4, and that is used to make phosphine, which is pH3, according to this equation. Calculate the amount of white phosphorus produced. So white phosphorus, so N of P4, we're only given the mass in this question, and we can easily work out the molar mass from the periodic table. So we will do 2.478 divided by 30.974 multiplied by 4, since there's a 4 here, so don't forget to do that. And bear with me 1 second. So that would give you the answer of 0.0200. So I'm giving it to 3 decimal places because 3 decimal places over there. Or 3 significant figures as well. So to be clear, this is the equation we have used is mass over molar mass. It's good practice to write that first as well. I've just kind of forgotten, but you should ideally write the equation before you substitute numbers. Now, in this case, assuming that P4 is a limiting reactant, and if you're not familiar with what a limiting reactant is, let's not worry about that right now. We will learn about that later. But assuming that P4 is a limiting reactant, if we know that P4 is 0.0200 moles, sorry, I forgot the units there, then if we wanted to work out the moles of pH3, for example, on the product side, we can also say that the N, or the moles of pH3 is equal to the same, because there's a 1-to-1 ratio between P4 and pH3. So whatever this is, assuming that it is a limiting reactant, that should be the same, theoretically. Okay, and now to mole fraction and mole percent. So mole fraction is the amount of one substance in a mixture divided by the amount of all the components of that mixture. basically this equation, mole fraction is represented as xi, and mole percent is just that times by 100. Once again, not something very commonly tested from my experience, but it's just good to remember. So I guess it would just show you what proportion of a mixture is a certain substance. You could also do percentage composition by mass, which is total mass of an element divided by total mass of compound. Sorry, this is not for, this specifically is not talking about mixtures. It's talking about a compound. So the mass of an element divided by the mass of the whole compound times by 100. Next, we're going to talk about empirical and molecular formulas. So a molecular formula is the actual number of atoms in a compound. I will talk more about that. And that's the molecular formula, sorry. And then this is empirical formula. It is the lowest whole number ratio of atoms in a compound. So to give an example, if we have C6H12O6, which is glucose, this is the molecular formula. But the empirical formula would be CH2O. And that's because the common denominator is 6 in all of these numbers, so we can just divide everything by that to get CH2O. There's an invisible 1 in front of each of these, but once again, we don't really say the 1, so we usually just leave it out and assume that it is 1. We can also, if we know the empirical formula and the molar mass, we can find the molecular formula by dividing molar mass by the mass of the empirical formula and multiply the empirical formula by the product. So basically, you would just take the mass of the empirical formula, and then you would divide that by m to get, and then, sorry, I'm just repeating myself. I think you probably will get exposed to this more in further questions, but I don't have an example here. So let's say that you have a formula that is like A to B, let's just say it's A to B, right? A and B being random elements. If you know the mass. So basically, I mean mass of the empirical formula, as in if I can go to the periodic table, and let's say in the periodic table it shows that A is 10 and B is 2 in the molar mass, in their relative atomic masses, then I can find the m of the empirical formula to be 12. And now, if I know that the m of the compound, say it's AXBY, say that the molar mass of the whole compound is 24. Then if I simply divide the mass of the empirical formula, the mass of the compound by the mass of the empirical formula, it will give you 2. Therefore, you can multiply everything here by 2. So, times 2 times 2. Therefore, the molecular formula should be A4B2. There are actually many ways to calculate empirical formula from different sets of data, and I'm going to explain that in a separate video because it is going to be a bit long if I include it in this video. So this is it for the first part of topic 1.2. I will see you in the next